All right, our second section of 11.2 is going to talk about permutations. And so normally, if I were in class, I would ask a couple of students to volunteer to tell us a joke. And I have to say it has to be a clean and appropriate joke. But since we're not in class, let's just imagine that we have Joe, Sally, and Paul. And how many different ways can these three people tell their jokes? Well, couldn't Joe go first, then Sally, then Paul, just like we have here? But then couldn't Paul maybe go first? Then it would be Paul, Joe, then Sally? And if Paul went first, then maybe Joe went last. That's a whole nother way of telling those jokes. Or maybe Sally wanted to go first, and then Paul, and then Joe. Or maybe Sally wanted to go first, but Paul wanted to go last. Whew! Taking these three people and rearranging them gives me a whole bunch of different ways these three people can stand up and tell us their joke, right? And how many different ways can that happen altogether? Well, that's what we're going to talk about in this section. It's called a permutation. So a permutation is an ordered arrangement of items that occur when no item is used more than once, so Paul didn't tell two jokes, and the order of the arrangements makes a difference. Maybe Paul goes first, maybe Paul goes second, or maybe Paul goes third. So when order matters, we call it a permutation. Let me show you another example of what a permutation is, and then we'll actually figure out how many different ways we can do it. Well, it says here, you need to arrange 7 of your favorite books along the small shelf. How many different ways can you arrange the books, assuming that order of the books makes a difference to you? So again, I don't know about you, but I like to kind of imagine what's happening. So I have 7 little spots here. And I know that I want to take and I want to put books on these little spots in my shelf. And so when I go to place books on my shelf, how many different books do I have to choose from the first time I go to place a book on the shelf? Well, doesn't it say I have 7 books? And so the first time I go to put a book on my shelf, don't I have 7 books to choose from? I'm going to pick one of them, but I have 7 different options. So now the next time I go to put a book on the shelf, how many books do I have left? Yeah, don't I have 6 left now because I already put a book on the shelf, so there's 1 less to choose from? I still want to put 1 book there in that second spot, but now I only have 6 options. How many different options, how many books do I have left to fit on the third spot on my shelf? Yeah, don't I have 5 now? And then 4, and then 3, and then 2, and then 1? And then this kind of ties back into our last section, where if I have 7 options for the first spot and 6 options for the second spot, and I want to put 1 book in each spot, how do I figure out how many ways to do this? Well, don't I use my counting principle to multiply all these together? I've got 7 times 6 times 5 times 4 times 3 times 2 times 1. Or what we might say is 7 factorial. Now that little looks like exclamation mark doesn't mean 7. It means 7 times 6 times 5 times 4 times 3 times 2 times 1. We really have 5,040 ways you can rearrange all 7 of these books. Now I don't know if anybody would do it that many times, but you have a total of 5,040 ways you could possibly do that. So if we go back to this Sally, Joe, and Paul example, if there are 3 different people that need to stand up in front of us and tell a joke, and we need to figure out how many different ways they could stand up, how many different people do I have to put in the first spot? I would have 3, right? And then I would have 2 people, and then I have 1 option for the last spot. And I could multiply those together and really say that there are 6 different ways that these 3 people could come up here, rearrange themselves, and tell us a joke. It's called a permutation when order matters, and we actually end up using the counting principle with it as well. So we just talked about factorial with 7 factorial, right? 7 times 6 times 5 times 4 times 3. What factorial means is that you're taking that number and multiplying it by every other number behind it until we hit 1. Okay? One other factorial notation that we might see is 0 factorial. It seems kind of silly, but 0 factorial really equals 1. I know that seems kind of silly, and if you have questions on that, you might want to Google it. It's a good kind of idea to kind of investigate on why that is. But 0 factorial equals 1. So anytime you see that, make sure you remember that. All right, let's do one last example in this video, just practicing that factorial notation. So if you look at example number 3, it asks us to evaluate without using a calculator what 8 factorial divided by 5 factorial is. Well, let's break it down a little bit. 8 factorial, remember, means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial means 5 times 4 times 3 times 2 times 1. Those are really big numbers without our calculator, right? And so what can we do to kind of help us out? Well, if we know from math that if we have a factor on top that's the same as a factor on bottom, we can reduce. So I can reduce a 1 from the top and a 1 from the bottom, numerator and denominator. I can reduce a 2 from the top and a 2 from the denominator. I can divide the top and the bottom both by 2. I can reduce the 3's, I can reduce the 4's, I can reduce the 5's, and that makes it a little bit easier because now all I have left is the 8 times 7 times 6. That might be a little bit easier without a calculator. Okay, go ahead and get your calculator. We can cheat on this one. What is 8 times 7 times 6? Yeah, 336. But because it says without a calculator, I would like you to show your kind of work on how you would set it up so that I know you know what 8 factorial really means and not just punching it into your calculator. Let's look at B. B says that we have 26 factorial divided by 21 factorial. Okay, here we go. What does 26 factorial mean? All right, 26, 25, 24, 23, 22, all the way to 1. Now you could write it out if you want to, but wait a second. Think about what's happening in the denominator. Don't we have a 21 factorial, which means 21, 20, 19, 18, and all the numbers down to 1? And won't the 1's on the numerator and denominator reduce, and the 2's reduce, and the 3's reduce, and all of the numbers will reduce, including the 21's? So can I at least stop at 21 and say, all of those numbers, the 21, 20, 19, and so on are going to reduce, instead of writing it all out? And so then I can see, without writing it all out, that we're just going to have a 26 times 25 times 24 times 23 times 22 left. Okay, we might need to use a calculator on that one. I got 7,893,600. All right, let's look at the last one here. C says, what is 500 factorial divided by 499 factorial? Oh man, please don't write out 500 times 499 bottles of beer on the wall all the way to 1. Sorry, I cracked myself up. What we can do is we have a 500 times a 499 factorial. Let's stop there because the 499 and every other number behind it is going to reduce. Let's stop there, cancel those out, and what's our final answer? Yeah, just 500, right? All right, the point of that example is just making sure you understand what that factorial notation means, and you can kind of simplify using that factorial notation. Practice those first couple examples, and we'll do on our next video here in a second, okay?